Hello friends, welcome to my lecture. Today we will discuss on the topic open set, closed set and countable sets. In this lecture we will learn to some theorems and corollaries on the open sets, limit point of a set, derived set, Bolzano-Weierstrass theorem and some examples. In this unit, in this lecture, first discuss on some theorems on the open set. The first theorem, prove that interior of a set is an open set. In the last period we discussed on what is meant by the interior of a point, what is meant by neighborhood of a point, what is meant by dilated neighborhood of a point, and some examples. Next, what is meant by interior point of a set. A point X is an interior point of a set S if S is the neighborhood of X. In other words, X is an interior point of the set S if there exists an open interval A comma B containing X and contained in S. Next, what is by interior of a set? Set of all interior points of the set is called the interior of a set. Yes. Next, what is by the open set? A set S is a set to be open if it is the neighborhood of each of its point. Okay. By using all these basic definitions to prove this theorem number 1. And these theorems prove that the interior set, set of the interior point is also an open set. By using the definition of the interior set, let S be a given set and S dash its interior. This is the symbol for the interior set. Interior points of the sets, there is the S dash. If S dash is equal to 5, and by the one remark, the every empty set is an open set. Therefore, S dash is a open set. When S dash is not equal to 5, this is the print mistake. S dash is not equal to 5 means the S dash is not empty set. Let X be any point of S dash as X is an interior point of S. The X be the any point of the S dash means X is the interior point of the set S, and by the definition of the interior point, there exists an open interval Ix such that X belongs to Ix subset or equal to S. But Ix being an open interval is the neighborhood of each of its points. Every open interval is the neighborhood of each of its points. This implies every point of Ix is an interior point of Ix. But Ix is the subset or equal to S. This implies every point of Ix is the interior point of S. Therefore, Ix is the subset or equal to S dash. This implies X belongs to Ix is a subset or equal to S dash. This implies any point x of S dash is the interior point of S dash. By the definition, we say that S dash is a open set. Always remember this corollary. It's a statement. The interior of a set S is an open subset of S. Okay. Second theorem. The interior of a set S is the largest open subset of S. So many subset of the S. All these are the open set, but interior of a set S is the largest open subset of S. Another statement of these theorems, that is the interior of a set S contains every open subset of S. Okay. Proof of these theorems, we know that the interior S dash of a set S is an open subset of S. By the last theorem we prove that. We prove that the interior set is an open set. Let us now proceed to show that any open subset S1 of S contained in S dash. Let X be any point of S1. Since an open set is a neighbor of each of its points by the definitions, therefore S1 is a neighbor of X, but S is the superset of S1, means S is also a neighbor of X. This implies X is an interior point of S. S is the neighbor of X, means by the definition X is an interior point of the set S. Again, this implies X is the interior point of S. This implies X belongs to S dash. S dash is the set of all interior point of the set S. Thus, X belongs to S1. This X belongs to S1. This implies proves that X belongs to S dash. Therefore, by the property of the subset, S1 is the subset or equal to S dash. Hence, every open subset of S is contained in its interior S dash. This implies S dash is the interior of S, is the largest open subset of S. Again, remember that this corollary statement, interior of a set S is the union of all open subset of S. Theorem number 3. Prove that the union of the arbitrary family of open set is also an open. Okay. Union of an arbitrary family of open set is also an open set. Let capital Z be the union of arbitrary family F. F is the set of all open set S lambda. Lambda belongs to capital lambda, is the set of open sets. Lambda being an index set. To prove that this G is the union of this arbitrary family of open sets, G is the union of all these open set, E is also an open set. Okay, suppose that this is the open set Z. S1 is the one open set in this family. S2 is the open set in this family. S3 is also. So in general, the arbitrary family of open sets. This F is the arbitrary family of open sets. It is the S lambda. Okay. This is the G is the union of all these open sets. on the in the all these are the subset of the real numbers. To prove that G is the open set, we shall show that for any point x belongs to G, any point, this is the arbitrary point x in this figure, for any point x belongs to this set G, this G is the union of all these open sets, it contains an open interval containing x, this is the open interval containing x. Let x be any point of G. Prove that this statement. Let x be any point of G, since G is the union of the member of this family of, there exists at least one member S lambda of this family which contains x. Again, S lambda being an open set, again by the definitions, the open set, there exists an open interval Ix such that x belongs to Ix, subset or equal to S lambda is the subset or equal to this G. Thus, the set G contains an open interval containing any points of this set. This implies G is an open set. And the proof. Again, theorem number 4. Prove that the intersection of the any finite number of open set is also an open set. And theorem number 3, that is the union of the arbitrary family of open sets is also an open set. But in this theorem number 4, the intersection of any finite number of open sets is also an open, not arbitrary family of open set, its intersection is open. But the intersection of any finite number of open sets is open. Proof of these theorems, let us consider the two open sets S and T. That is the finite number means 2 or 3 or 4 or 100. That is the finite number of open set. And in this theorem, first consider the two open sets S and T. This is the set S, and all these sets are the set of the real numbers. This is the second set T, suppose. And if the intersection of these two sets equal to phi, suppose. In this figure there is no phi. Intersection of these two sets is not equal to phi. But suppose that the intersection of these two sets S and T, that is also equal to phi. And by the one remark, the empty set is also an open set. Therefore, the intersection of these two sets is an open set. If S intersection T is not equal to phi, from these figures, these two sets, its intersection is not equal to phi. And let x be any point of this intersection. Suppose this intersection point, and x is the any point of this intersection space. Now, x belongs to S intersection T. This implies the x belongs to S intersection T. This implies the x belongs to S and x belongs to T. Both the sets includes. This is the x belongs to the intersection of these two sets. Okay. This implies S and T are neighborhood of the x, because S and T are the open sets. Because the S and T are the open set, means the S and T are the neighborhood of the point x. This implies S intersection T are the neighborhood of x. Okay. S and T are the neighborhood of x means the intersection of these two sets is also again the neighborhood of the x point. But since x is any point of x intersection T, x is an arbitrary point of these intersections, and therefore S intersection T is a neighborhood of each of its point. Hence, the S intersection T is open. The proof may of course be extended to a finite number of sets, 3, 4, 5, so in that. It is the finite number of open sets. Note, the above theorem does not hold for the intersection of arbitrary family of open set. That is only this theorem is hold for the intersection of finite number of open set. Consider one example. The open set Sn is equal to the open interval minus 1 by n belongs to the natural number set. And the intersection of all these arbitrary open sets, that is also equal to 0. Means that is the S1 is equal to the open interval minus 1 by 1 plus 1 by 1. S2 is equal to open interval minus 1 by 2 plus 1 by 2. S3 is equal to minus 1 by 3 plus 1 by 3. So in general, an intersection of all these open sets, that is only the single point set, that is the 0 single element set 0, and consisting of the point only 0. And by the one remark, the single point set is not open set on the real lines. Okay. Second point, the limit point of a set. First, what is meant by the limit point of a set? A real number zeta is a limit point of the set S. S is the subset of the real number set R. If every neighborhood of xi contains an infinite number of members of S. Okay. Xi is the limit point of the set S. S is the subset of the R. If every neighborhood of xi contains an infinite number of members of S. Thus, xi is a limit point of S. If for any neighborhood n of xi, the n intersection S is an infinite set. Okay. Every neighborhood of xi contains infinite number of members of A means suppose that the capital N is the neighborhood of the point xi, then the intersection of this neighborhood set and the S is an infinite set. A limit point is also called a cluster point. In other words, the limit point is also called a cluster point, condensation point, or an accumulation points. Second definition of the limit points. This is the first definition, and second definition of the limit point. A real number zeta is a limit point of the set S if every neighborhood of zeta contains at least one member of S other than xi. Every neighborhood of xi contains at least one member of S other than zeta. Okay. Evidently, from the first and second definitions, a limit point of a set may or may not be a member of the set. Limit point of the any set may or may not be a member of the set. Some limit points is a member of this set, some limit point is not a member of this set. Further, it is clear from the definition that a finite set cannot have a limit point. Finite set cannot have a limit point. Also, it is not necessary that an infinite set must possess a limit point. Number of limit points. Okay. A sufficient condition for the existence of a limit point is provided by Bolzano-Weierstrass theorem, which is discussed in the next sessions. The following these two definitions, definition 1 and definition 2, evidently the definition 1 implies definition 2 by the definition of the 1 and 2. By the first definitions, the every neighborhood of zeta contains an infinite member of S, means the at least one member of the neighborhood of every neighborhood of zeta other than yes. Therefore, the definition 1 implies the definition 2. But let us now prove that the definition 2 implies the definition 1. Let zeta be a limit point of the set yes. Okay, zeta is the limit point of the set yes, and such that every neighbor of zeta contains at least one point of s other than zeta by the second definition limit points. By the second definition of the limit points, every neighbor of zeta contains at least one point of s other than zeta. Let this is the open interval zeta minus delta 1 and zeta plus delta 1. Okay, be one such a neighbor of zeta. This open interval is the neighbor of the zeta point, which contains at least one point, say x1. x1 is not equal to zeta of the set S. And let x1 minus zeta mod of x1 minus zeta is equal to suppose delta, and this delta 2 is less than delta 1. Now consider the neighborhood zeta minus delta 2. This to this point, zeta minus delta 2, and so this is the zeta minus plus delta 2. Now consider the neighborhood, this open interval zeta minus delta 2 and zeta plus delta 2 of this point zeta, which by the definition 2 of a limit point must have one point. Suppose that this point x2 of the S other than zeta. By repeating the argument with the neighborhoods, that is the open interval zeta minus delta 3, zeta plus delta 4 of the zeta. Similarly, the open interval zeta minus delta 4, zeta plus delta 4. Similarly, again the open interval zeta minus delta 5, zeta plus delta 5 of the zeta, where delta 3 is equal to mod of x2. This is the second point, x2 minus zeta, x3 minus zeta, x4 minus zeta, x5 minus zeta, so in general. And so it follows that the neighborhoods, the open interval zeta minus delta 1, zeta plus delta 1 of this zeta point contains an infinite member of the set S. Therefore, hence the definition 2 implies the definition 1. In the first part, automatically the definition 1 implies definition 2, and in the second part the definition 2 implies the definition 1. Okay, it is instructive to note that a point zeta is not a limit point of the set S if there exists even one neighbor of zeta not containing any point of S other than zeta. Okay. Next, what is meant by the derived set? The set of all limit points of the set S is called the derived set of S and is denoted by S dash. Okay. Give a bounded set having no limit point, infinite number of limit point. For examples, the set I is the set of integer, has no limit point. Set I has no limit point for a neighborhood, that is the m minus 1 by 2, m plus 1 by 2, m belongs to I. M is the integer, an integer, m is the arbitrary integer in the set I. Find the neighborhood, that is the open interval m minus 1 half, m plus 1 half contains no point of I other than m. This neighborhood, there is no any point of the interval I other than m. Therefore, this set, this is the arbitrary point, this is the derived set of I, is the null set phi. There is no any limit point of this set I. Second example, the R is the real number set, and every point of the real number set is also an limit points. For every neighborhood of any of its points contains an infinite of members of R, and therefore the interior set, that is the limit point set, that is the R. Okay, means the derived set is equal to itself, that is the R dash is equal to R. Third examples, every point of the set Q is the rational number set, is a limit point. All points of the rational number set is also a limit point. For between any two rationals there exists an infinity of rationals. Further, every irrational numbers is also a limit point, the limit points of the rational number set Q. Or between any two irrationals there are infinite many of rationals, and thus the every real numbers, means that is the rational numbers as well as irrational numbers, all these are the limits points of the set Q, and therefore the derived set, the set of limits points of the rational number set, that is the Q dash, is equal to R. Fourth example, the set 1 by n belongs to n has only one limit point, and that is this is the 0. That is because in this set there is the 1 by 1, 1 by 2, 1 by 3, 1 by 4, all these are the elements of this set. This is the infinite sets. This is the infinite set, but this infinite set has only one limit point, and this limit point is the 0. 0 is not belongs to this set. 0 is not the member of this set, but this is the limit point. 0 is the limit point of this set, but 0 is not the member of this set. Okay. Every point of the closed interval AB is its limit point. So take any intervals, closed intervals. Now all the points of the closed intervals is its limit point, and a point not belongs to the interval is not a limit point. Means outside of this interval, all the points is not the limit point, but all the point of these intervals is also an limit points, and thus the derived set, this intervals, that is the interval AB dash, is equal to itself. This is the open intervals. Every point of the open interval AB is its limit point. The end point A and B, both are also limit point, but the end points A and B are not the member of these intervals. Means the limit point sets of the open interval AB is equal to the set of all points of this interval, and the end point is also, means that is the derived set of this open interval, that the A comma B dash is equal to the closed interval A comma B. This is the only the further statement of these Bolzano-Weierstrass theorems for the sets. This is the necessary condition for the limit point. Every infinite bounded set has a limit point. Give any infinite bounded set, it has the limit point. Okay. Some examples. Like example number 7. S and T are the subset of the real numbers. Then show that the first S is the subset or equal to T. This implies the derived set of S is the subset or equal to derived set of T. And second point, derived of union S union T is equal to union of derived of the set S and T. Solution. First, in the first part, S is subset or equal to T. Then prove that S dash is the subset or equal to T dash. Number 1, if S dash is the empty set, then evidently S dash is the subset or equal to T dash. Suppose that S dash is not equal to phi, and let zeta belongs to S dash and n be any neighborhood of zeta. S dash is the set of limit points, derived set S dash, means that is the, let zeta belongs to S dash and n is the any neighborhood of xi, then by the definitions n contains an infinite number of members of the set S, but S is the subset or equal to T, means the n contains infinite many members of the T also. And this implies this, by these conditions, this implies the zeta is the limit point of the T, that is the zeta belongs to T dash. And thus zeta belongs to S dash. This implies zeta belongs to T dash. Hence, by the definition, by the property of the proper subset or subset, that is the S dash is the subset or equal to T dash. And the first part. In the second part, prove that if the given conditions prove that the derived set of the S union T is equal to union of the derived set of the S and T. The first, now S is the subset of S union T. This implies by the first part of this examples, S is the subset of S union T. This implies S dash subset are equal to this S union T dash by the first and T is the subset or equal to S union T. Again, this implies this. Consequently, the union of the left sides is the subset or equal to right hand sides. Now we proceed to show that conversely prove that this the derived set of S union T is the subset or equal to union of derived set S and derived set T dash. If this set is not equal to, that is equal to empty first, then evidently this set is the subset of this. This is the brain mistake. That is the equal to phi. When suppose that this set is not equal to phi, then let zeta belongs to this set. Zeta belongs to the derived set. Now zeta is the limit point of this set. Therefore, every neighborhood of zeta contains an infinite number of points of the set S union T. This implies every neighborhood of zeta contains infinite many points of S or T or both. This implies zeta is the limit point of S or zeta is the limit point of T. Or this implies again the zeta belongs to S dash or zeta belongs to T dash. This implies that zeta belongs to S dash union T dash. And thus zeta belongs to the derived set of S union T. This implies that zeta belongs to union of derived set S dash and T dash. And consequently, this is the S union T dash is the subset or equal to S dash union T dash. From 1 and 2, it follows that these two are the equals. Thus, the derived set is derived set of the union is equal to the union of the derived set. Another one examples. If S and T are the subset of the real number set R, then show that the derived set of intersection of these two sets is the subset of S intersection T. And the second part, an example to show that the derived set S intersection T, derived set of the S intersection T, and intersection of derived set S and T, that is T dash, may not be equals. Now, the first consider S intersection T is the subset or equal to S. This implies by the first examples, the first article, that is the derived set of this left hand sides is the subset or equal to derived set of the right hand sides. And S intersection T is the subset or equal to T. Again, this implies by the first examples. And consequently, the derived set means that is the derived set or set of the limit point S intersection T is the subset or equal to intersection of the S dash and T dash. and second parts, this is the S dash and T dash. Okay, and let S is equal to the open interval 1 comma 2 and T is equal to open interval, that is over 2 comma 3. Show that. They give an example to show that these two are not maybe equals. I mean that is, suppose that the first set S is equal to the open interval 1 2, second set T is equal to open interval 2 3, and so that the S intersection T, the intersection of these two sets, that is also equal to phi. This implies the derived set of this intersection. The limit point of the phi, that is the MT, that is the phi dash, and that is also equal to phi. So that S dash is equal to, first find, this is the left hand side. Okay, S intersection T dash is equal to phi. This is the left hand side. One part, its value. Secondly, find the value of S dash, means the derived set of S, that is the set of the limits points, that is S dash is equal to, and the open interval limit point set is the closed interval, that is the S dash is equal to the closed interval 1 2. Similarly, the set of the limit point of the open interval, that is the closed interval, that is the T dash is equal to these closed intervals, and the intersection of these two sets, that is also equal to 2. 2 is the common point. This is not empty, but this is the empty. This proves that these two sets may not be equal. Thus, these two not equals. In this lecture, we learn to the sum theorems and corollary on the open sets, limit point of these sets, derived set, Bolzano-Weierstrass theorems, and some example. Thank you.